Exam style questions on cosmology, focus on Edexcel IAL Unit 5 Physics syllabus. Okay, so first question, how to measure the luminosity of a standard candle? You know that standard candle means a star with known luminosity is called standard candle. But how do we know its luminosity? We say a star or an astronomical object with known luminosity is called standard candle. But how do we know its luminosity? How to measure its luminosity? Without knowing the luminosity, we can't use the standard candle to measure the distance of far distant galaxies. Normally, we can use this method to find the distance of a galaxy which is at a 100 megaparsec. Different books they say it is slightly different values, but up to almost 100 megaparsec we can use standard candles to measure the distance of a galaxy. But we should know the luminosity of the standard candle. Even we say a star or an astronomical object with no luminosity, how to measure the luminosity of that standard candle you must know. Okay, so normally we say astronomical objects, certain astronomical objects could be used as standard candle. Mean the well-known standard candle is Cepheid variable. Cepheid variable means it's a variable star. It periodically expands and contracts. Due to its expansion and contraction, its luminosity varies periodically. There are many Cepheid variables in our galaxy. Easily we can measure their distance by using trigonometric parallax method. So the Cepheid variables, they have a periodical variation in expansion and contraction that causes periodical variation in their luminosity. So there's a relationship between luminosity and the period of expansion and contraction. Higher the luminosity, greater the period of expansion and contraction. Those are relationships are there. That's called luminosity period relationship. There's a graph, well-known graph is there. That graph shows for Cepheid variables. If we know the luminosity, wait, I'll tell you how to measure the luminosity. But if you know the luminosity of the star against the time period of expansion and contraction, the best fit line is a straight line. Okay, this we call calibration by using nearby Cepheid variable. The various Cepheid variables, those are closer to us in our galaxy. We make this calibration graph. The calibration graph is luminosity of the Cepheid variables against their time period of expansion and contraction. So there's a luminosity. How did we measure the luminosity of these Cepheid variables? Those are closer to us. That you should know, right? So how do we measure the this luminosity of these Cepheid variables? Those are closer to us. We can measure like this. Normally we measure the intensity of the Cepheid variable. We can measure the intensity by using light meter or something like that. We measure their intensity or radiation flux by using something like light meter. Normally it's measured by using satellite telescope out of the Earth's atmosphere, because Earth's atmosphere can scatter the radiation. To avoid it, by using telescope satellites, telescopes in the satellites, we can measure their intensity, right? Then what we do, we can measure their distance, because I told these Cepheid variables are closer to us. These Cepheid variables are closer to us in our galaxy, Milky Way. So we can measure their distance by using trigonometric parallax method. So we know their distance also. So intensity or radiation flux both refers the same. We know that. The distance, we know that. So by using the inverse square law, I equal L over 4 pi d squared. We know the intensity, we measured it. We know the distance, we measured by using trigonometric parallax method. So we can calculate the luminosity of nearby standard candles, that is nearby Cepheid variables. We can easily measure their luminosity if we are using Cepheid variable as a standard candle. Right, then what should we know? So we know the luminosity of the nearby Cepheid variable. So there I told already there are many Cepheid variables closer to us in our galaxy. So we can measure different Cepheid variables, their luminosity and their period of expansion and contraction. So if we plot a graph of their luminosity against period of expansion and contraction, we will get a straight line through the origin. So this graph is a calibration graph. This data is obtained by using Cepheid variables, those are closer to us, or standard candles, those are closer to us, right? Now we need to measure the luminosity of a far distant Cepheid variable which is in some other galaxy, far away, up to, we can use this method up to 100 megaparsec, yes. So how to measure its luminosity? A star, a galaxy that consists of a Cepheid variable. How can we measure this standard candle's luminosity? We can't just say the standard candle or Cepheid variable in far distance galaxy is a known luminosity. Normally we might say, but you should know how to measure the luminosity of this Cepheid variable which belongs to a far distance galaxy. Far distance galaxy means not more than 100 megaparsec. How to measure this luminosity? If I measure this luminosity, if I am able to measure its luminosity, then I can measure the distance of this particular Cepheid variable from us. Okay. How to measure the luminosity of this particular standard candle? How to measure it? Okay, we can measure like this. Observe its period of expansion and contraction, or observe the variation in its intensity. You can receive the radiation from it, and you can plot a graph how its intensity, right, when the luminosity varies, intensity also will vary same way. So we can receive the radiation from the star and plot a graph how its intensity varies with time. So if you plot a graph how its intensity, we are receiving the intensity, not the luminosity. We receive the radiation and we measure its intensity from Earth or by using the satellite telescope. And this is the time, not time period, time. How its variation, intensity is varying. So you will get a graph something like this. From this graph, measure its time period, right? You can get time period, 2 or 3 time period, and find the average time period of that particular Cepheid variable. Then using this time period, from this graph, the calibration graph, you know the time period for this far distance Cepheid variable. So use this graph, and from this graph, measure the luminosity. Now we know the luminosity of this. So this Cepheid variable's luminosity, we know that. So we call it as standard candle, because star with its known luminosity. How do we know its luminosity? Because we found it by using this method. Keep it in mind. This is the way we find the luminosity of a far distance Cepheid variable. Okay, so this is the answer. If the standard candle is Cepheid variable, so we know that standard candle is a star or an astronomical object with known luminosity. So one of it is the Cepheid variable, could be used as a standard candle. So if it is a standard, if the standard candle is Cepheid variable, then this is the method we use to measure the luminosity of that specific standard candle, which is Cepheid variable. I already explained this, right? Okay, but there are other astronomical objects, they also could be used as standard candles. For example, type 1a supernova, type 1a supernova. Those are not in your syllabus, so I don't want to go in detail. Type 1a supernova, there are some other different types of astronomical objects, stars are there. I'm not going to talk about them, not in the syllabus. But type 1a supernova is something like, is a binary star. That means two stars rotate about their common center of mass. One of it is, if it is a white dwarf star, then it can gain photons from the next star, and when the mass of the white dwarf star increases beyond a specific value, it explodes. That explosion is called type 2 supernova. Anyway, I don't need to go in detail about it. But now this is the intrinsic characteristic of the Cepheid variable. So the intrinsic characteristic of the Cepheid variable means it periodically expands and contracts. So the luminosity of it, the average luminosity actually, the luminosity of it or the average luminosity of it and the time period has a relationship, that is a graph. I already told you. So that is the property of Cepheid variable. Like that, type 1a supernova also has its own intrinsic property. We can use that property to measure the luminosity of that particular standard candle when we use type 1a supernova as a standard candle. So like that, different astronomical objects are there. They have their own intrinsic properties. We need to use their own intrinsic properties to measure their luminosity. This is the detailed one in your syllabus for Cepheid variable if you use it as a standard candle. But type 1a supernova, not in your syllabus. I don't want to go in detail about it. But the question is very general. How to measure the luminosity of a standard candle? So it's not saying anything about which type of, what is the standard candle, whether it is a Cepheid variable or whether it is a type 1a supernova or some other astronomical objects are there. It's not specifically telling the type of standard candle. So in that situation, you can write a answer like this. This is the way you can write, but it's not a good answer. But see, that's not a, sorry, it's not a good method to find the luminosity. There will be larger uncertainty in that type of measurements. But since if the question is something like this, the question is not specifically focusing on the type of standard candle, you have to give the answer very generally. So that general method, now I'll tell you how to write that. Okay, so the general method, whether it's a Cepheid variable or type 1 supernova, the first method is okay that we use for Cepheid variable also. That method is same thing like earlier what I explained. Measure the distance of the standard candle if it is closer to us within 100 PC. Measure its distance by using trigonometric parallax method. First, if the standard candle is closer to us, measure its distance by using trigonometric parallax method. Then measure the intensity of the radiation from that standard candle by using satellite telescope. Then by using I equal L over 4 pi d squared, since we know d we measured by using trigonometric parallax method, intensity we measured by using satellite telescope, then you can calculate the L by using L equal I times 4 pi d squared if the standard candle is closer to us within 100 PC. Right. But if the standard candle is beyond that, we can't measure its distance by using trigonometric parallax method. So in that situation, the method I am going to tell is not accurate, but somewhat we can explain that in the exam because the question is not specifically focusing on the type of standard candle. So there what we say, receive the radiation from the standard candle and disperse it and identify the most intense wavelength. You understand? Receive the radiation from the standard candle, disperse it and identify the most intense radiation and measure its wavelength lambda max. Measure its wavelength lambda max. Okay, after measuring the lambda max, by using Wien's law, lambda max T equal to 2.898 10 to the power minus 3 meter Kelvin. By using Wien's law, find its or calculate its surface temperature. Until now, okay. Measure its surface temperature. Right. Now only the uncertainty comes. After calculating the surface temperature, use Hertzsprung-Russell diagram, HR diagram. Now the HR diagram, you can see HR diagram in which the y-axis is relative luminosity, L over L naught. X-axis is temperature. You can see the plot of the HR diagram. It's a wider graph. It's not a proper graph. It's a wider region. That's a problem. That gives the larger uncertainty. So what we do, we know the temperature, surface temperature of it. So by using the x-axis, where the temperature you obtain, you find the relative luminosity. But when you are finding relative luminosity, there will be larger uncertainty because this central, the main sequence is shown on a wider region. That is the problem I told. There will be large uncertainty. But anyway, we can, the examiners, they accept this method. Normally the past paper questions, they accept that. So measure the, by using this HR diagram, find the relative luminosity. So you know the relative luminosity. Since you know the relative luminosity and you know the luminosity of the sun, you can calculate the luminosity of the standard candle, which is more than 100 pc, where we are unable to measure its distance by using trigonometric parallax. This is the answer you have to give. Okay, so the uncertainty is due to wider region of the center part that represents the paint sequence stars. Okay, so this is the answer you have to give. The same question appeared in October 2022 paper, question number 13. The same question appeared in October 2022. Yes, October 2022. Question number 13. So the question is, the average distance between galaxies is many times greater than the size of our galaxy, right? Okay. Astronomers use standard candles to determine the distances to other galaxies. Describe how astronomers determine the luminosity of a standard candle. So there, the type of the standard candle is not specified. So luminosity of the describe how astronomers determine the luminosity of the standard candle and can use this to determine the distance of a nearby galaxy. Distance of a nearby galaxy means not where we are unable to use the trigonometric parallax. Nearby galaxy means a galaxy which is beyond our galaxy. Nearby galaxy means not more than 100 megaparsec. If it is more than 100 megaparsec, we can't use standard candles method. We have to adapt the next method, that is Hubble's law and the Doppler shift method. Redshift in the absorption spectrum and the Hubble's law we have to use if it is more than 100 megaparsec. So here the question says how use this to determine the distance to a nearby galaxy. Nearby galaxy means which is somewhere less than 100 megaparsec. How to measure the distance? So there first you should say how to measure the luminosity of the standard candle in that particular galaxy. Then use the inverse square law. I'll write the answer now. Okay, so this is the answer for that particular question, because there the type of the standard candle is not mentioned. So generally we write this way. Okay. Okay, the second question, Polaris is a Cepheid variable closer to our Earth, and the recent measurements show that the Polaris may be significantly closer to Earth than previously thought. So explain how this means there's a improvement in the measurement of distance of Cepheid variable, which is Polaris. Earlier they thought it was far away, but now later they found by using more advanced measurements, proper measurements, they found it is closer to us. So how this change in measurement of distance in this Polaris, explain how this would have significant impact on the measurement of luminosity of far distant galaxies. Okay, so I told that far distant galaxies means where we have to use this Cepheid variable methods, right? Okay, we can't use trigonometric parallax method. Okay, so Cepheid variable here, the standard candle is specified Cepheid variable, right? Okay, so we have to adapt the properties of the Cepheid variable. What is the property of the Cepheid variable? It has a periodic expansion and contraction, and the higher the luminosity of the Cepheid variable, average luminosity of the Cepheid variable, the time period also will be higher. And if you plot a graph of luminosity or average luminosity on y-axis and their time period on x-axis for different Cepheid variables, the graph will be a straight line. Okay, that is true for any Cepheid variable. They obey this graph. We call it normally luminosity time period graph, or we can call it as luminosity time period calibration graph. Right? Okay. So there, what happens? They are using Cepheid variable closer to Earth. They would have used that data. They would have used this Polaris, one of the data, when they are plotting the graph. I told that the previous question. We plot a graph of average luminosity against time period by using the Cepheid variables. Those are closer to us. Okay, now what's the impact on this graph due to the improvement in the measurement of distance? Now they found the Polaris is closer to us. It's used as a one of the data for the calibration graph. Calibration graph means luminosity against time period graph. Okay, what change will happen in that graph if we think like that? Okay, so we know we measure the distance by using trigonometric parallax method. There they found this Polaris is closer to us. We measure the intensity by using one of the instruments, light meter or something like that. We measure the intensity. The measurement of intensity has no change. It's accurately they did. Okay, only the change happened in the distance, right? So then we use I equal L over 4 pi d squared to calculate the luminosity of this Cepheid variable closer to us. So there is no change in measurement of intensity, but the distance measurement has dropped now. We know the Polaris is closer to us. So when the distance gets smaller, no change in I means the luminosity, what we thought earlier, the luminosity of the Polaris, but now we know the luminosity of the Polaris is going to drop now. The luminosity of the Polaris will be lower than previously we thought, right? Then what should we do? Think about the graph. We have several data. We plot the graph by using many different Cepheid variables closer to us. We plot a graph of luminosity against time period. There, the time period of the Polaris has no change. Only change occurred in the distance measurement, right? So earlier graph maybe for a particular time period, the luminosity, earlier we thought it was the distance is higher, luminosity is higher. So earlier the graph what we got may be something like this. But for a particular time period of the Polaris, we know that now the luminosity is dropping. I already explained it because the distance is getting closer. Closer means we measured and found it's actually not as what we thought earlier. It's closer to us. So luminosity will be smaller. So for the same time period of the Polaris, now the luminosity is going to be smaller. This is the earlier graph. Now the graph, something like, only this one is dropping. So if you draw the best fit line, there is nothing wrong. So wrong means there is nothing wrong means only the data slightly changed. So the new graph might come something like, it will slightly drop below. So the new graph is going to be best fit line something like this. So now what's going to happen? The graph is going to be like this, is going to drop a little bit. The gradient will drop a little bit. Okay, so when the gradient drops like this, the question is how is it going to affect the luminosity of far distance Cepheid variable? What we do, we measure the far distance Cepheid variable, its period we measure, because we can't measure its distance, because we are going to measure the distance. That's the purpose of this method. So we measure the period of expansion and contraction of far distance Cepheid variable. There is no wrong in that measurement. Then what we do, we use this graph. We know the far distance Cepheid variable's time period. We measure it accurately. Earlier, maybe that time period is this one, right? So earlier we got the luminosity of that particular far distance Cepheid variable somewhere here, but blue graph is the new graph. This is the new graph. According to the new graph, the luminosity will be lower. So the luminosity of the far distance Cepheid variable also will drop. Okay, so that's the answer. So the answer, what should we say? We can say like this. When the distance of the Polaris become closer, or new measurement of the distance of Polaris becomes smaller than the expected value, or earlier we thought, the luminosity of the Cepheid variable also will become smaller. When the luminosity of the Cepheid will become smaller, the graph of luminosity against time will have a lower gradient. Therefore, there is no change in the time period of the far distant Cepheid variable. Hence, its luminosity also will become lower than expected. Okay, this is the answer. So far distant means that distance is below or lower than 100 megaparsec, where we can use Cepheid variable as a standard. And if it is more than 100 megaparsec, we can't use Cepheid variables. We have to adapt this next method, that is use the Hubble's law and the redshift by using redshift in the absorption spectrum. So we have to use the Hubble's law and the Doppler effect if it is more than 100 megaparsec. But this question is based on below 100 megaparsec. But it's called far distance star because more than the distance which where we can't use trigonometric parallax. Okay, the second part of the same question I put separately. The same question, but the second part is same information, same data, but the second part is explain how this would have significant impact on the measurement of distance of far distant galaxies. Far distant galaxies, again I am telling, the distance is lower than 100 megaparsec, where we are able to measure the distance by using trigonometric parallax method. So how is it going to have impact on this particular measurement, distance measurement? Okay, already I told the luminosity of the Cepheid variable in the galaxy, far distant galaxy, is going to be lower than what we thought earlier, right? Now, how do we measure the distance? We know the luminosity of the Cepheid variable. We found it, it's lower than expected. We measure the intensity. There's no mistake in the measurement of intensity that we measure by using satellite telescopes. So by using I equal, if I use I equal L over 4 pi d squared, if I use, the measurement of I has no change. It's perfectly accurate, nothing happened. But only we know, the previous part I told, L has dropped now. L has dropped means D will drop. The distance will be lower than what we thought earlier. I am not writing it, so you have to say the second part. Already we know the previous part, L is dropping. There is no change in the measurement of intensity I. So according to I equal L over 4 pi d squared, the distance of that far distance Cepheid variable will become lower than what we thought. That's the answer you should write. Okay, third part of the same question, last part of the same question. So we know that because of the variation in the measurement of Polaris, we know it has getting smaller, closer to us. We know the luminosity of any far distant Cepheid variables will become lower, and we know that the distances of any Cepheid variables in the far distance galaxies are going to be smaller. That means the distances of far distance galaxies is going to be smaller because we know that how do we measure the distance of far distance galaxies? We measure the distance of the Cepheid variable in which the galaxy, the Cepheid variable. Then we say the distance of the Cepheid variable which consists of the distance of the galaxy which consists of the Cepheid variable is also at the same distance. Say for example, we measure the from Earth, we measure the distance of the Cepheid variable. This is the galaxy. We measure the distance of the Cepheid variable from us. Then we say distance of the galaxy from us also the same, because compared to this distance, the variation due to its dimension is negligible, because the distance between the galaxy and Earth or us is much larger compared to the dimension of the galaxy. So we measure the distance of the Cepheid variable, then we say the distance of the galaxy which consists of that Cepheid variable is also the same. So we, second part we answered, the distance of the Cepheid variable is going to drop. That means distance of the galaxy from us is going to drop. So any far distance galaxy which is lower than 100 megaparsec, but their distances calculation is going to be lower than what we thought earlier. You understand? We already know that the luminosity is dropping for the Cepheid variable. Already we showed it in the second part. The distance of the Cepheid variable is dropping, means distance of the galaxy from us is dropping, right? Then how is it going to have impact on the age of the universe? Okay, so Hubble, he measured the redshift of the galaxies. They are receding. You know, universe is expanding. I already put a separate video about it. Universe is expanding, accelerating. The expansion is accelerating. So there will be redshift in the absorption spectrum from the galaxies. So he by using Doppler effect, he measured the speed of recession of the galaxies. There is no change in the speed of measurement, because speed of measurement is done by using the redshift and the Doppler effect. There is no change in that measurement. So he plotted a graph of y-axis speed, x-axis distance. Okay, so the graph what he plot earlier, before they identify this correction, the graph what they plot may be something like this, right? For a particular, any particular galaxy, its speed of recession may be something like this. So its distance is something like this. Now what is happening? After this correction, this distance, we know the distance of any Cepheid variable is getting closer than what we thought earlier. That means any galaxies are getting closer. The measurement of distance of any galaxies will become smaller than what we thought. That means for their speed of recession has no change. Say for example, for a particular speed of recession, earlier the distance was this much. For the same speed, now the distance is going to be smaller, like this. So the graph should be like this. So what's going to happen? The gradient of the graph will become larger. This is the new graph after the correction of distance in the Polaris, distance of the Polaris. So the new graph for a particular speed, earlier the distance we thought is larger. Now for the same speed, we know the distance of any galaxy is getting closer. So arbitrarily, if I take one galaxy, we know that's closer. Second galaxy also, that will be closer. So the gradient of the graph is going to be moved down. So gradient move means Hubble constant. The gradient of the speed distance graph is the Hubble constant. So the Hubble constant is going to be larger or greater than what we thought. Age of the universe, we know that 1 over h naught. So Hubble constant is getting smaller. Greater means age is going to drop. So age of the universe will be lower than what we thought. That's the final answer. Age of the universe will be lower than what we thought. Okay, this is the answer you should write. Okay, third question. Capital X is a Cepheid variable closer to Earth, and the recent mesh analysis shows that the star X means the Cepheid variable X, is covered with significant amount of dust. Explain how this would have significant impact in the measurement of far distance galaxies. Okay, so we are using X as one of the data to plot a graph of luminosity against time period. Okay, so we know that, so I can little bit explain more fast now. So we use this as one of the data. So there is, when we consider the equation, so there is no change in the measurement of distance. This is one of the star. X is a star closer to us, means we can measure its distance by using trigonometric parallax. Nothing wrong, it's perfectly correct. The problem is I equal L over 4 pi d squared. we use this method. So distance we measured by using trigonometric parallax method, that is has no problem, it's correct. We measured the intensity by using satellite telescopes. Since the luminosity is lower, actually is more because it's covered with dust. For example, if you have a light meter at school, keep the light meter in front of a bulb, you will get a particular intensity. Cover the bulb with a tissue paper or cover the bulb with some transparent tissue paper or something like that, and now measure the intensity, you will get a lower value. So the intensity what we are measuring is actually lower than actual value. The intensity what we are measuring now is lower than actual value. We use that intensity to calculate the luminosity. So there is no change in D. Our intensity we measured lower value, but actual value should be larger. We calculated the L by using this measurement, and we calculated the L by using L equal I into 4 pi d squared. So the measurement of intensity has dropped due to the dust covering the Cepheid variable x. So the luminosity value will become lower than actual value. So our measurement has a lower value of luminosity than the actual value. Right. So the time period of expansion and contraction of the x has no change. So we plot a graph. We plot a graph by using y-axis luminosity against time period. So by using this data where we know intensity of x is lower, when we use that graph for a particular time period, we got a graph something like this. But this is the graph we got it. But for that particular Cepheid variable x, it has a specific time period. For that time period, the luminosity, we got this value, but actually that luminosity should be higher. Because the intensity we measured is lower, luminosity we calculated becomes lower. So the actual graph should be, the actual value of luminosity of that particular Cepheid variable x should be greater than what we measured. So the actual graph must be this way. The actual graph must be somewhere like this. It won't exactly pass through it basic line when there's a change. Maybe it will have a greater grade, something like this. The actual graph should pass. Okay, so this is the wrong graph. This is the correct graph. Actual graph should be, this is the one. This is the wrong graph. Wrong graph means earlier graph with the dust. Wrong graph we can say, or this is the graph what we obtained with the dust. But actual graph should be this one. Now we are measuring, focusing a telescope to far distant galaxy, and we search and find a Cepheid variable, and we measure its time period. Now after we find the time period of it, for that particular time period, we earlier got luminosity of that far distance galaxy this much, but actual luminosity should be this much. So the actual luminosity of a far distance galaxy, the Cepheid variable in the far distance galaxy will become greater than what we are having now, should be greater. So if the luminosity of far distance galaxy will become greater means we are going to measure its distance. So we measure its intensity from the far distance galaxy, that has no change. I equal L over 4 pi d squared. Intensity measurement is correct. Luminosity, earlier we had a lower value. So the distance d squared is equal to L over 4 pi I. So d is going to be square root of L over 4 pi I. So for a far distance galaxy, I has no change. Now luminosity, we used a wrong data earlier. We thought that is correct, but we know there is dust is covering it now. So actual luminosity of the far distance Cepheid variable is greater. So distance of far distance galaxies will become greater than what we thought earlier. That's the answer. So distance of the far distance galaxies will become greater than what we thought earlier. What we thought earlier means when we were using the data when X is covered by dust, We had a particular value for far distance galaxies, the distance we measured, but now we know the distance what we measured, we have underestimated due to the dust. Actual distance should be more than what the value we have now. Okay, so this is the answer for this particular question. Intensity is underestimated because of the dust covering the X. Therefore, the luminosity of L is underestimated. Therefore, the graph of luminosity against time period has lower gradient than the actual gradient. Hence, the luminosity of the far distance variable is underestimated. According to I equal 4 pi d square, the distance of far distant galaxies are underestimated due to the dust covering the Cepheid variable X, which is used as one of the data to plot the luminosity against time period graph. Okay, so I hope these are exam type questions. It will be useful to you. Okay, right. Bye.